Hi, this is Kara Tierney from Monroe Community College, and in this video I just want to bring together some of the things that we talked about in the previous videos about quantum numbers and the quantum mechanical atomic model. So let's just review what those quantum numbers are. So n is our first quantum number. Electrons within the same shell have the same value of n. And so that shell, if we think of like the first shell, we can think about an area that's closer to the nucleus, and as we get farther out, those shells get bigger. Now within the shell, there are subshells, okay? And that is what's defined by our next quantum number, L. And so subshells are within shells, or sublevels are within levels, and the electrons with the same values of N and L are all the same type of subshell. So we can think of this as a shell, and within that we have our subshell, and then the subshells are made up of orbitals, and the orbitals each have a capacity of 2. And now the number of subshells within a shell depends on your shell number, and then the number of orbitals within a subshell depends on the type of subshell. Within the subshell we have orbitals. Electrons within the same orbital have the same 3 first values of quantum numbers, and then within each orbital there are 2 electrons, and we differentiate between those electrons in an orbital with our last quantum number, which is our spin number. So if we take just a broad look at what's going on with the structure and step away from the quantum numbers themselves for a little bit, we can take a look at this chart. And in our first shell, okay, there's one subshell, the 1s subshell. Each s subshell has 1 orbital, and its electron capacity is 2. So if we look at the second shell, n equals 2, there are 2 subshells, 2s and 2p. We can figure out the electron capacity of that shell by looking at the number of orbitals within each of those subshells. So every s subshell has 1 orbital, and every p subshell has 3. So we multiply each of those by 2 to get their electron capacity. So 1 times 2 is 2. So every s subshell can accommodate 2 electrons, and every p subshell can accommodate 6. So in the entire n equals 2 shell, there's the capacity for 8 electrons. When we look at the third shell, there are 3 subshells possible: 3s, 3p, and 3d. Every s has 1 orbital, every p has 3 orbitals, every d has 5 orbitals. We multiply those each by 2 to get their electron capacities, so 2, 6, and 10, and we add them all up to get the capacity for the third shell, and that would be 18. Why don't you take a moment and try this for the fourth shell? Okay, if you're not finished, press pause. If you are, let's check. So there are 4 different subshells in our fourth shell: 4s, 4p, 4d, and 4f. And in subsequent larger shells, there are other types of subshells that could exist beyond S, P, D, and F. They're going to follow the same pattern. So you'll notice that our number of orbitals follows the pattern of 1, 3, 5, 7. They're all odd numbers. So beyond the F, the next type of subshell would have a capacity of 9. So it would just follow that pattern, even though we don't have a specific name for that subshell. So if we take a look at the electron capacities for all of these, we just multiply them by 2. And what we get is, when we add them all together, we get 32. So this kind of gives you an idea of the number of orbitals within the subshells that are within the shell. So we're all just getting more specific as we're going from shells to subshells to orbitals. So why don't you give problem example 4 a try. Pause the video now and press play when you're finished, or if you get stuck. So now we're in this more fictional fifth electron shell. It has 5 subshells. We haven't defined that 5th subshell yet, but like we were talking about before, we can use that same pattern of number of orbitals for the different types of subshells. So the max number of electrons within the entire shell, if we take a look at our 4th subshell, all we're doing is we're just adding one more subshell to this. This would have 9 orbitals. Since we're following our pattern, it would be maybe we could call it a G subshell, and so that means it would have 18 electrons. So our capacity for the 5th subshell would be 50. And if we're looking at the max number of electrons in a 5d orbital and a 5d subshell, notice that there's a very, very specific difference between B and C, and I just want to point that out because you have to be very careful with what the question is asking. So the max number of electrons in a 5d orbital is different than in a subshell because the subshell includes all 5 different orbitals. If we're just looking at one 5d orbital, it has a max number of electrons of 2 because all orbitals have a capacity of 2 electrons. If we're looking at the subshell, then we're going to look at all 5 different orbitals, and so that would have a capacity of 10 because we're multiplying the 5 orbitals by their capacity of 2 electrons. So you have to be very careful at the words in the questions that you're answering. I'd like you to give your turn a problem. It's similar to one that we were looking at in the last video. Give your best shot at this one. We're going to discuss the answer in class. Be sure to come with any other questions as well, and I'll see you there in class.